Carrying on looking at our motion and using calculus, now going to look more at the idea of integrating functions of time. Got a velocity time graph here, so you notice it's x dot there rather than displacement. Now, if I want to find the change in displacement, okay? Now, change in displacement is like the definite integral. So displacement is a complete integral from 0 to 4, whereas change in distance would be like the area of the graph. And so I'd have to break it up into its different areas. So remember, displacement or distance is the derivative, is the integral of velocity, which means it's the area under the curve. Okay? So let me just recap that again. Area under the curve of a velocity graph would tell us distance. So again, I guess to summarize all of that, if we're finding change in displacement, that's the complete integral from starting point to end point. Whereas if it's change in distance, we have to break the velocity graph into above the axis, below the axis, and add the different areas together. So a similar thing will happen with acceleration. This would be the acceleration graph that comes from that particular velocity graph. If I wanted to find change in velocity, it would be the complete integral. Whereas change in speed, again, I would have to break it what's above and what's below. And so the below one, you'll notice I've got there as negative 0 to 2 because it's below. So all right, well, let's talk a bit about derivative graphs and what sort of features we're looking for. So displacement, we know the first derivative would be the velocity graph, and the second derivative would be the acceleration graph. So they might not actually ask us to say, hey, draw the derivative of this graph, but they might give us a displacement time graph and say, hey, draw the velocity graph. It's the same question. So stationary point, what do we know about stationary points? They occur when the first derivative is equal to 0. So therefore we will get an x-intercept on the first derivative or the velocity graph. An inflection point. What do I know about inflection points? Well, inflection points, the second derivative is equal to 0. So therefore, I must have ended up with a stationary point at the first derivative. Because logically, if you look at the line above, stationary point went to x-intercept. If the second derivative is going to be x-intercept, it must have come from a stationary point. So you look for an inflection point on the original graph, it'll be a stationary point on the first derivative, or the velocity graph, and it'll be an x-intercept on the second derivative or acceleration graph. Okay, we know when the curve is increasing, the first derivative is positive. So this curve will be above the x or the t or whatever the horizontal axis is. Decreasing, of course, would therefore be negative. If it's concave up, then we know the first derivative will be increasing. Why do we know that? Because if we go to the second derivative, if it's concave up, the second derivative is positive. Looking at 2 lines up, well, hang on, positive came from increasing, so therefore the one in the middle must be increasing. So the first derivative will be increasing and the second derivative would be positive. Concave down, therefore, would be decreasing because the second derivative would be negative, and so the negative must have come from a decreasing curve. All right, types of graphs. If the graph is a horizontal line, then when I integrate it, I must get an oblique line, a line at an angle. If I differentiate it, it's going to be the x-axis. Because differentiate a constant, horizontal line, we're saying y is a constant, differentiate it, you get 0. So you get the x-axis. If you've got an oblique line, so some line at an angle, integrate it, we're going to get a parabola. Integrate a linear function, you get a quadratic function. Differentiate it, we'll get a horizontal line. If the original graph is parabolic, integrate it, we're going to get a cubic. Differentiate it. Oh, as I say, inflections will be at the turning point. And the oblique line when we differentiate it. Okay, so integration is area. That's how you find the area under a curve. But on a velocity graph, total area for distance, whereas total integral will be displacement. On acceleration graph, total area will be speed, whereas total integral will be velocity. All right, let's have a look at a couple of questions. Another trig graph for this velocity time graph in this case. So 2 minus 4 cos t, v is in meters per second, and t is in seconds. At what time during this period is the particle at rest? Well, they've already given me a velocity graph, so I don't have to do anything to it. It's at rest when velocity equals 0, so we're just solving 2 minus 4 cos t is 0. Cos t is a half. We're just looking between 0 and 2 pi, so we're going around the circle once. And so we're in the first and the fourth quadrant. Acute angle would be pi on 3. So our angles, or our times in this case, pi on 3 seconds and 5 pi on 3 seconds. Remember, the answer must be in radians, because now we're saying this is the time. The time is pi on 3. So it is whatever, 3.14159 divided by 3 seconds, a very short piece of time. If I had put that answer in degrees, I'd be saying t is equal to 60. Well, 60 seconds is a lot different to a bit over 1 second. Answer must be in radians, because whenever we're dealing with motion and calculus with trig, the angle measure is radians for it to work. Okay, so particles at rest at pi and 3 seconds, again after 5 pi and 3 seconds. So what's the maximum velocity? A question I personally hate. We were discussing a bit about this yesterday. I hate it when they say maximum velocity, but they did in this particular year. I personally think they should say maximum speed. But anyway, let's have a look. So, I can use my knowledge of the graph. Okay? They've given me a velocity graph. I know the amplitude of 4 cos t is 4. So minus 4 cos t, if I was to draw it, would go between minus 4 and 4. But this one's shifted up 2. So this particular graph would go between minus 2 and 6. So what's the maximum velocity? Well, in this case, I don't have to worry about the issue, which I'll talk about in a sec, because clearly the biggest velocity in this case is 6 meters per second. Where I hate this question, so they got away with it this particular year because it was positive and it was 6 as well. Imagine if that had ended up between negative 6 and 4. What is the maximum velocity? Yeah, yet it's going faster at negative 6. Because remember, all the negative signs telling this direction. And that's why I don't like them saying maximum velocity. A better question is maximum speed. Because what do you want? You really want to know just how fast it's going. All right? So, as I say, a question like this, it didn't matter, because the maximum speed and the maximum velocity turned out to be the same. If you do get in that situation, explain your answer. If you go for the one that I just mentioned and you say negative 6, explain why you've gone for that answer. Because at the end of the day, they just want to understand whether you understand the question. So if you've clearly gone for that, but you explain why you've gone for it, then yeah, a reasonable marker will go, yeah, fair enough, that's not a problem. All right, let's sketch that velocity time graph. Amplitude, as I say, was 4 units. We've shifted it up 2. It's upside down because it was negative 4 cos. Period's 2 pi. I'll mark my divisions off every pi on 2. Okay, so there's my axes. Cos normally starts at the top of the amplitude. This one's been shifted up 2 and flipped upside down. So let's put an axis in at 2, flipped upside down, so we'll be starting at negative 2. But then we go up to the axes and continue up and down. There's our graph. Calculate the total distance travelled by the particle. So from 0 to pi on 3, it's below. From pi on 3 to pi, it is above. Notice I've swapped the limits around here and made it positive. And the only reason for that, I guess, is because now when I go minus, I've got pi on 3 on the bottom of both of them, and so I can go minus 2 lots of when I substitute in pi on 3. So I've substituted in naught, because that's the top of this one, plus I've substituted in pi, because that was the top of the second one, but then I've said minus 2 lots of, because pi on 3 was on the bottom of both. It's only a little bit of saving of working out. It's not that big a deal, but it's something I tend to do. What does that all work out to be? Oh, look at that answer. Is that beautiful? What, 2 pi minus 2 pi, keep going. Ah, yes. A very predictable answer of 4 root 3 plus 2 pi on 3 meters. This one, they've given us a graph. It's an acceleration time graph. So what's it doing? Moving along the x-axis again, very convenient. Initially, it's at rest at the origin. There's the particular graph. Write down the time at which the velocity is our maximum. Now, they're not asking us to draw the velocity graph. We should be able to tell that from this graph. Because remember, velocity is the integral of acceleration. So what are they actually asking me? Right? So it's saying, when is that integral a maximum, the value of the integral? So when is the area the maximum? Well, clearly it's going to be at 2. Because as soon as I go past 2, this is all going to now subtract. So remember, below is negative. So the area, it's starting at 0, I guess, and then we're getting a little bit. At 1, I have the rectangle 1, 3, so I know that it's the area is at 3. Then it's going to be plus this triangle, so it's getting bigger. It's getting bigger. So I get at 2, but now I would subtract that triangle. So the value of the integral, because we're talking about the integral, of course, not the area, the value of the integral is getting less. Or another way of looking at it, I could say velocity is a maximum when dv dt is equal to 0. Right? Because it's the first derivative of velocity. Well, what's dv dt? Acceleration. When is acceleration equal to 0? Oh, look, there it is at 2. So velocity is a maximum when t equals 2 seconds. So using that second method, then we definitely get that answer of 2. All right. At what time during that interval is the particle furthest from the origin? So now we're talking about displacement. But again, all we've got is this acceleration graph. Okay, so what's it asking? When is displacement a maximum? If you were going to find a maximum, what would you do? Well, I know it's a maximum when the velocity is equal to 0. Well, how can I tell that from this graph? I've got an acceleration graph. Velocity is the integral of acceleration. So we're now saying at what point would the integral, so the overall integral, equal 0. So we have to solve the integral of acceleration is equal to 0. When is the area above equal to the area below? All right, so we can just look at the shapes, and we talked about that just before. We'll say, oh, there's that rectangle and the triangle, which would match with the rectangle and the triangle underneath. So logically, it must be at t equals 4. Those two areas would balance out. So by symmetry, we can see that's going to be at t equals 4. So we haven't actually, we've used calculus to solve the problem, but we haven't actually done any calculus. We've just looked at the picture and used a little bit of logic about, okay, here's our answer. 2007. Much more fun. Look, it's got curves and all sorts of interesting shapes here. This one is a velocity time graph. Velocity time graph. And they've highlighted some particular points. There's 5, 0, 6, -5. And after time is 6, it just keeps going at a constant velocity, they're telling us. Okay. It was a sneaky way of getting a Simpsons rule question in there, because we're going to find the area under this curve, but we don't know what the function is. But we do know some points on it, so we can use Simpsons rule. So using Simpsons rule, so they gave us a hint just in case we're going, how the heck am I going to work out that area? Estimate the distance travelled. Because the distance travelled, this is a velocity time graph. So the distance travelled will be the area. And they're just going from 0 to 4, so it's all above, so we don't have to worry about splitting it up. Okay. Remember, h on 3, the end values, 4 times the odd ones, 2 times the even ones. Let's draw up a table of values. We've only got 3 values we can work with. We know 0, 0, 2, 1, and 4, 5. So it'll be 1 times the end one, and just 4 times the middle one, and we haven't got any other ones to work with. So subbing that in, h, well, the distance between my values here is 2, so it'll be 2/3, 0 plus 4 plus 5, so we get 6 metres. Okay, they've told us the object starts at the origin, during which time is the displacement decreasing. Okay. Well, we know a function is decreasing when the first derivative is less than 0. So we're now saying, hey, this graph we've got, when is it less than 0? When is it below the horizontal axis? Okay. Well, just looking at our picture, we can see, well, that happens when t is greater than 5 seconds. Estimate, and it will be an estimate because that area we just worked out using Simpson's rule was an estimate. Estimate the time at which the object returns to the origin, justifying your answer. So you couldn't just randomly go, oh, I think it's at 10 or wherever. So again, it's saying when is displacement equal to 0? When is the area above equal to the area below? Right? Displacement's the integral of velocity. We're solving when is that integral equal to 0? Area above, area below. So I've just redrawn the picture over here. Okay, I'm going to use symmetry. Those triangles, so from 4 to 5 is going to be the same as 5 to 6. So they're going to cancel out. We just worked out from 0 to 4. It was on the screen before. What did we work it out was? Well, I've probably got it here, haven't I? There we go. Is 6. So our question really now is, when is this rectangle after t equals 6 going to have an area of 6? So area 4 has to equal 6. 5a will equal 6. So about 1.2. Well, that's not our final answer, of course. We've got to add that on to the 6. So around about 7.2 seconds. 7.2 seconds. Sketch the displacement graph. Okay. There's our velocity graph. We're going up a level, so we're integrating. We need to draw displacement. I like to put these below each other, so I can just transfer directly down the important information and plot those. So the first thing I've done there. I've also labelled in some of the things we found. We found when displacement was 6 and 8.5 and things like that. So we can get that information in there. So the first thing I'm going to plot in, the object is initially at the origin. So I know I'm starting t equals 0, x equals 0. Okay. We know that when t equals 4, x equals 6, that was our estimate for the displacement. So I'll plot that point in. We said by symmetry that this triangle, the triangle above, was the same as the triangle below. So therefore, at t equals 6, it must return to 6. So I know that point as well. Area of the actual triangle we said was 2.5. That's why I've drawn in 8.5 there. So it must have gone up to 8.5 and then back down to 6. So I can plot that point in. We estimated that displacement was back to 0 when t was 7.2. So plot that point in. Now this is looking at the graph, because I've got to draw in some sort of line here, but it's not going to be a straight line, because this, to get an oblique line, it must have come from a parabola. That's not a parabola. So there's going to be some sort of a curve here. Now, what I notice is that between 0 and 2, it's shallower than between 2 and 4. So that means that, here we go, it covers more distance between 2 and 4. So I'm going to, at 2, plot a point lower than 3. I don't know exactly where it is, but I'm going to put it lower than 3 because I know it covers more distance between 2 and 4 than it does between 0 and 2. Because it's going quicker. It's steeper. Now, we know that when t is greater than 6, velocity is a constant. Well, if velocity was a constant, it must have come from a straight line, some oblique line. Okay, so I've drawn in the first part of my graph. That is going to be a oblique line joining up these 2 points that I knew. There's the rest of my graph. And so I've got some sort of curve coming here. This I've made parabolic between 4 and 6, because between 4 and 6, this is an oblique line. Integrate the oblique line, you would get a parabolic shape. So that bit's nice, parabolic. This is just some curve where I knew that this is going to be going up slower than that part. So I just made it look a bit smooth to draw in. And there is a displacement time graph. Isn't that fun? All right, let's try another one. 2005. Odd sort of graph, but there it is. It's another velocity time graph. What do they want us to do? Oh, so initially it's the origin again. At what time is displacement a maximum? Displacement a maximum. So again, we've got to be thinking to ourselves, right, displacement will be a maximum when the area is at most positive. Also, when velocity is 0. So I can think of either of those two ideas. Well, we've got a couple of times velocity is equal to 0. Which one's going to give us maximum? Well, t equals 2, because I'm thinking in their context, area most positive is the one up top there. Yeah. At what time does the particle return to the origin? Okay, return to the origin. When is displacement equal to 0? So when is the area above equal to the area below? Again, we've got an odd-looking shape here between 1 and 3, but it certainly looks symmetric. So I'm going to assume those areas are the same. I really can't do anything else. So this rectangle here, from 0 to 1, would have an area of 2. So I need to work out when the rectangle below there would go. So that's 2. I'm just calling that area A. I have no idea what it is, of course. By symmetry, below will also be A. So the question is, when is that 2? Oh, well, that's easy enough to work out. Just got to work out the width of the rectangle. 2W will equal 2. Ooh, that's tricky. W is 1. So it looks like it returns after 4 seconds. Draw an acceleration graph. An acceleration graph. So right, there's a velocity graph. This time we're differentiating. So I'll draw it underneath, plotted in some key points there to match up. So what do I know about acceleration? Okay. Horizontal lines. Remember, we're differentiating to get there. Differentiate a horizontal line, you're going to get the x-axis. You're going to get 0. So I know that on my acceleration graph, I'm on the x-axis at those points. Okay. From 1 to 3, I'm guessing, okay, best I can do, I think it's a cubic. You know, you've got a turning point here, an inflection point, a turning point down the bottom. So I'm just going to make a guess that that's a cubic. So therefore, when I differentiate it, I must get a parabola. Okay. I know it's below the axis because here we're decreasing. So if we're decreasing, the derivative would be negative. So it must be below the axis. Okay. Well, again, I'm assuming this is all nice and symmetric. So if I've assumed this piece is a cubic, then this I'm going to assume is part of a cubic as well. And so when I differentiate this, I will get half of a parabola. And this time it'll be above the axis because the curve is increasing. So the derivative would be positive. Whoop. So there's, well, a poor attempt at half a parabola anyway. And there we go. A very strange acceleration time graph. Okay, let's have a go at some of it.